Let's look at this problem. We have a circuit with an EMF device, but that's connected to the circuit with a switch. Switch has been open. We are assuming that it has been open for a long time, and then it is closed at time t equals 0. And there are a few things that the question is asking us to find. And the currents in all branches at time t equals 0. That's one of the questions. And the currents in all branches at time t equals infinity. And then there are a few other things. The rate of change of the current at time t equals 0. A specific current in here. And then the inductor energy. So the last part is also at t equals infinity. Let me write it in here. At t equals infinity. Find the energy stored in inductor labeled L1 at t equals infinity. So the first thing that we should notice in here is that this circuit is very complicated. So as a result, if I'm asking something about this circuit to you in an exam or, I don't know, homework, you cannot find the currents as a function of time. That's basically too complicated for you. It can be found, but it appears that since there are two inductors in here, there are two time constants. And so that's definitely it's a more complicated question. You can also see that there are three loops in here, and writing down the equations would also be very complicated. So it doesn't appear that there's an easy solution as well. In any case, so that's too hard. So as a result, that means that when I'm asking what happens at time t equals 0 or t equals infinity, that's basically the information. You have to use some other information to compute these. So computing the current as a function of time is out of the question in any case. So therefore, we are going to use some physical principles to answer these questions. So that's kind of obvious actually. At time t equals 0, the only information that we have used is the continuity of the current. So there was no current on the inductors before the switch is closed. So therefore, immediately after the switch is closed, the currents on the inductors would be 0. So that's the only information that we have. I'm going to discuss part B. At t equals infinity, of course, the currents have reached their final values, in which case there should be no EMFs on the inductors, right? So at one time, of course, you say that the currents are equal to 0. At another time, at t equals infinity, you say that the EMFs are equal to 0 because the currents are no longer changing. So let's go ahead and start solving. So I'm going to start with part A. So that's the circuit again. But this time, as we have said, the currents on these branches are 0. So let me just label these currents like that. So current on that branch, let me also call this as I2. So the information in here is that the information, let me write explicitly that this is for time t equals 0. So at t equals 0, immediately after the switch is closed, we know that current I1 and the current I2 is equal to 0 because the current flowing on an inductor is always continuous. It cannot change. It cannot have a jump discontinuity. So as a result, these currents should be equal to 0. Which means that, if you want to think about some kind of an equivalent circuit, I can think of it as an equivalent circuit like this. Let me quickly draw these. I don't connect these 2 points. So there's a resistor in here and there's another resistor in here. Normally there's an inductor in here, but I don't connect them because if I don't connect them, then there would be no current that would be passing in here as well. So this I1 current would be 0 because there is no wire that's connecting these 2 points. That's essentially the same. So whatever the current in here is, in the main branch, is going to flow through this resistor R1, pass from this mid branch, and then pass from this resistor labeled by R2, and then pass from this one. That's essentially what it is, what the solution of the question is. So there are actually a sequence of branches where the whole current is flowing and no current is flowing on the branches that contain the inductors. All right, so therefore we can then write down the loop rule. Obviously, this is our loop that we are going to choose. So in the loop rule, the sum of the EMFs is equal to the sum of the current times the resistances. So the EMF is EMF. Current times resistance is I times R1 plus I times R2 plus I times R3. So the EMF is 12 volts and the current is, I need to insert in numbers, so I just chose all the numbers in a simple way so that the initial current is 2 amperes. Right, that answers the first part. You can also see what the currents are in all branches, so as a result I'm not going to show it in here. So that was part A. So let me write part A in here. Current is equal to 2 amperes, and we know from which places the current flows. So I'm going to erase now everything in here, and then talk about part B. So that's basically the question is, what is the rate of change of I1 at time t equals 0? Sorry, it's a misplaced question mark. What's the rate of change of the I1 at time t equals 0? So as a result, we have something like this. If I plot I1 as a function of time, let me show it like that. The current was 0 before t equals 0. After t equals 0, of course, it starts from 0, but it starts rising. So, of course, eventually it's going to reach to a final value. So this question is basically asking the slope at that point. So I need to find the slope in here. That's essentially what it is asking. It's not asking the slope or the rate of change of the current or the derivative in here at an arbitrary time. So some people get confused about this kind of a question. So they kind of assume that they need to find the current as a function of time and then take the derivative and then compute it like that. No, it is not like this. So basically, there's some kind of a physical quantity that somehow depends on this rate of change of the current at this time. And we have to use that quantity, and it's obvious what that quantity is. So let's remember this. EMF, let's say it like this. The EMF on the inductor L1 is given as this expression. So as a result, if I can compute what that EMF is, I can then find what this thing is. So again, I'm going to draw an equivalent circuit in here, but this time I'm going to draw a slightly different one. All right, let me quickly draw all of these resistors. So we have said that we can replace this inductor by an EMF device. There is actually something in there, but I can think of this as equivalent to an EMF device. There is also an EMF device in here, but no current is passing right at that time, at the initial time. So there are these points in here. Let me call these points as A and B. These points A and B. So as a result, you can see that the potential difference between points B and B, I mean, if this was just an ordinary EMF device, I can express the potential difference like this. So I'm going to write it down like that. This is VBA. The potential difference, that's VB minus VA. That would be equal to the EMF. I don't know if this is positive or negative. Just keep this in mind. I'm just writing it by just looking at this expression in here, this picture in here. If this was just an ideal EMF device, then we would say that the potential difference across its ends would be equal to the EMF. But of course, in reality, we know that this EMF is generated by some other way, so therefore this is not really a potential difference. But in any case, that part is not important. So as a result, I relate it to I relate the EMF to a property on the circuit. Okay. Next, what I do is I just compute this potential difference this time by going over this resistor in here. I think it is easier to do this for VAB because there's a current on the resistor in here. This is the resistor with resistance R1. So VAB is equal to I times R1. So as a result, then I can find this potential difference. So therefore, I can find the EMF. So let's do this. So VAB is, the current is 2 amperes. And the resistance is 1 ohm. So therefore, there's a 2 volt potential difference between these 2 points. VAB is 2 volts, but A is at a higher potential than B because on a resistor, when you go along a positive current, the potential drops, which means VBA is negative. So B is at a lower potential than A, so therefore VBA is negative, so therefore this is minus 2 volts. That's essentially what this question needs. This is the thing that you should use to answer that question. So I'm going to go back to this equation again. So let me erase the upper part in here. Sorry about this. So we have found that EMF of the device in here is, so that's minus 2 volts. That's equal to minus the inductance is 0.1 Henry. Let me write Henry in there. Henry. And we have the rate of change of the current at that time. So just keep in mind that this is the initial potential difference between the points A and B at t equals 0. And therefore, this relates the rate of change of the current at t equals 0. So from here, you can see that di1 over dt, that's the answer to part B. The rate of change of the current at time t equals 0 is equal to 20. Unit should be volts per Henry, but probably it is better to express this as amperes per second. Let me add in here that this is positive, okay? It's kind of obvious that it is positive, which means that at t equals 0, the current on that inductor actually just starts to increase in the downward direction. So that's something that you could have expected at that point. So you can do it in a similar way. You can also compute the rate of change of I2, for example. In that case, let's see, the potential difference between these on this resistor is at t equals 0 would be 2 ohm multiplied with 2 amperes, 4 volts. So therefore, at t equals 0, there is an EMF produced in here which is equal to 4 volts. From here, I think we are also going to find the rate of change of I2 would also be 20 amperes per second at the initial time. In any case, so these two were about time t equals 0. So let's then pass to the questions at t equals infinity. At t equals infinity. The switch has been closed for a long time ago, basically. So this is the circuit. So what's important in here is that, of course, I1 and I2 have final values. So that's the physical principle that we are going to use. So that means the rate of change of the current, each current is equal to 0 because they have reached their final value, so they don't change anymore. Which means that the EMFs on the inductors, either inductor, would be equal to 0. Which also means that the potential drop if you think about the potential drop between these 2 points would be 0. So these 2 points would have the same potential. And I can do the same thing for this resistor now. So the potential drop on that resistor would be 0. And since the current going down the resistor would be equal to the potential drop divided by the resistance, I mean the current in here would be, let me do it like this. I don't know, let's just call this, for example, I3. So that's basically VAB divided by R1. So this point is A, or this point is A, and that point is B, or this point. This is just a wire, so therefore it doesn't matter B refers to which point, so both of them have the same potential. So so potential drop divided by the resistance, so therefore this is equal to 0. So that means, and I'm just going to show it like that. This is I4, this is I3. So I'm just going to erase this information because these are irrelevant now. So these two currents are equal to 0. So as a result, in that case, we have this kind of a situation. So we have an EMF device in here. We have an inductor in here, wire, and another inductor, wire, and a resistance. And the current doesn't flow in this branch or that branch. So I can take them out, just forget about these branches. There are some resistors over there, but since these 3 points, or let's say these 3 points, or I don't know, these 6 points all have the same potential, so therefore there cannot be any current flowing in from this point to that point because there's a resistor over there. So that means, let me call the current in here as I prime. So that I prime is the current flowing in these branches at this time. So since only the resistor in here is R3, and since there are no potential drops in here on the inductors, basically the loop rule will say that the EMF is equal to I prime times R3. So that's 12 volts. R3 is 3 ohms, so therefore the I prime is equal to 4 amperes. So part C has the answer of I prime is equal to 4 amperes. Alright, so the part D was about the energy that's stored in this inductor at time t equals infinity, but that's that has a very simple answer. So energy on inductor 1, let's say, that's going to be 1/2 of L1 times I prime 1 squared. So that was 0.1 Henry, and the current is 4 amperes. So the 4 amperes squared. So that's, as a result, this energy would be 0.8 joules.